All right, so we have to talk about this unique indeterminate form, but it is going to behave just like the other indeterminate form, which is 0 over 0. And these typically happen when you're approaching infinity. So let's do this with an example. Let's say the limit as x approaches infinity of 4x cubed over 5x to the 6 plus 2x squared minus x plus 10. Okay. Direct substitution is really an interesting thing here, and we don't really know what it means to cube infinity or take infinity, multiply it by 5 after you raise it to the 6th power. But we can talk about the end behavior as x approaches positive infinity. This numerator approaches positive infinity. So we know that much. This is an odd-degreed polynomial that has a positive leading coefficient, so its right end behavior is infinity. In the denominator, you have a polynomial. It's an even polynomial, even-degreed polynomial, with a positive leading coefficient, so its right end behavior is also infinity. And so here we are. We have an indeterminate form again. So what can we do? Yeah, we can take derivatives. So you can say this is the limit as x approaches infinity of 12x squared over 30x to the 5th plus 4x minus 1. And again, this is going to be an indeterminate form. This is just infinity over infinity. So we'll do that again. This is the limit as x approaches infinity of 24x over 150 x to the 4th plus 4. And again, that is infinity over infinity. So what do? We do it again. Yeah, this is the limit as x approaches infinity of 24 over 600 x cubed, which is 24 over infinity, right? Is that, if we're just to substitute in here, the right end behavior of 24 is 24. It is constant. It stays the same. Okay? The right end behavior of 600x cubed is infinity. So in the end, what can we conclude that this is? This is 0. Okay. Yeah. Okay. Right. Right. Okay. So really, that's a nice analytical way of going through and showing this. There's a hand-wavy argument. Okay. I don't write out what's the hand-wavy argument. What do you mean always going to equal 0? Yeah, if the rate of change of the denominator grows faster than the rate of change in the numerator, then eventually we can conclude that that will go to 0 at the right end. Oh. So really, from the get-go, I could have said that. The limit as x approaches infinity of 4x cubed over 5x to the 6th plus blah. And I write blah there because it doesn't even matter. It doesn't even matter. It's like it doesn't even exist. So really this behaves like the limit as x approaches infinity of 4x cubed over 5x to the 6th. And since you can see that you can, take 3 of the x cubed, 3 of the x's out of the numerator and cancel them with 3 of them in the denominator, you can see that goes to 0. Because all that blah stuff didn't even matter. It doesn't even affect end behavior. So it really introduces an idea. I mean, here's a different example. What's the limit as x approaches infinity of 4x to the 16th plus 500x minus 6,000 over x to the 16th plus 1 million? Really, how does this behave? Yeah, this is an infinity over infinity, and we could Lhopital it a number of times until we could work with this algebraically and cancel some of the variables in the numerator with some variables in the denominator. What's another way I can write this? Yeah, this is really behaving at infinity just like 4x to the 16th over x to the 16th. Really, because all of that stuff doesn't matter at all. Yeah, Chris.
Wouldn't it just end up being 4 then?
In this case, it would just end up being 4. And you can support that using Lhopital's rule. Okay? But really, what this does is it allows us to talk about rates of change in the numerator and rates of change in the denominator. Okay? And since these were going at the same exact rate, there's a horizontal asymptote at y equals 4. And that's found by the ratio of their leading coefficients. Yeah, Danica.
What if you had like 4x cubed over 5x to the 5th?
So the limit as x approaches infinity
Yeah.
of 4x cubed over 5x to the 5th?
Plus
After or still in the denominator?
still the denominator.
Okay.
But just x to the 4th. So that's second.
Plus blah, whatever.
But it has to be x to the 4th. So if it's greater than that, x to the doesn't matter.
Doesn't even matter. So long as it's written in standard form, then I know that the first term is going to be my highest power exponent, and everything will be descending in powers to the right of that. So really the only thing that starts affecting it is this, the greatest. And the blot doesn't even affect the end behavior. This is unique to what's happening at infinity. Okay. Yeah, Chris. Question.
So basically, with this rule, would we be able to just like single out the first kind of exponent, like the numerator, and then the first coefficient, and that's on in the denominator?
I don't understand your question.
So like, say you had the 4x squared over 5x to the 6 plus blah, you'd just be able to single out those only two.
Yeah, we could just say, you can argue that it behaves the same. That's why we said that all of this to the right of our leading terms didn't even matter. At infinity, when we're approaching infinity, that doesn't even affect the graph. So yeah, you can rewrite it like this and argue that. Or you can do it analytically. If you are doing a very formal proof, then you would want to do Lhopital's rule. Okay? And then this gets a little bit different because you don't always have polynomials in the numerator and the denominator. Okay? Sometimes you have e to the x in the denominator. In fact, that's an exponential. So what do you guys think grows faster? Does a polynomial grow faster, or does a exponential grow faster? An exponential, really, because the exponent is the variable, whereas a polynomial, the exponent is fixed. Okay, so I hope this kind of sheds some light on what we can do with some hand-wavy arguments. I need to stop the video because I can only do 15-minute videos.